Hello, everybody. My name is Marina Skimanich. I'm the Soil Moisture Program Specialist for NIDIS. I'm going to be speaking very briefly today about modeled output soil moisture data and products, and then very briefly after that, a little bit about blended products. So what models are we talking about? Well, these are land surface models, or LSMs, you might hear of that, and they are our best representation of a complicated hydrologic system. So in these models, there are physical and statistical equations used, as you can see there on the right. Pretty complicated. If you can read that, you're in the club. And those equations are used to simulate the flow of water and energy between the land, vegetation in many cases, and atmosphere. And as part of these land surface models, there tend to be two components: the hydrological model that would be linked to atmospheric models to get that full circle of water movement. The water balance approach is what's focused on here. We are looking at the change in soil water storage that's a result of incoming fluxes such as precipitation minus outgoing fluxes, that would be evaporation, transpiration, movement to groundwater, etc. And there are just a very wide range of land surface models that can provide soil moisture data, ranging from very simple to very complex, based on a number of factors. One important one is the number of soil layers. In the case there on the right, you can see the NOAA MP schema has 4 soil layers. In addition, there's a question of the number of hydrologic components that might be included. For example, in terms of dynamics, is snow considered? And if so, how many layers? Is evapotranspiration considered? How is vegetation engagement with water factored in? There's a lot of complexity that can come from that. Even if that's all consistent from model to model, there are a lot of different assumptions about how to handle those dynamics and what kind of parameterization to use to support the model. In addition, different models have different geographic coverage. Obviously, some are CONUS only and others go globally, etc. Some are just regional. And then there are different application targets. In some cases, modelers are building for research, and in other cases for operations, and that will affect the way they develop the model. Well, there are a number of model enhancements and extensions that are worth having just a sense of. One of them, atmospheric forcing, is quite standard at this point. This is the use of precipitation and other meteorological data as inputs to the land surface model. So this way the model doesn't run its own little box, but actually is bringing in actual meteorological conditions to help inform soil moisture and other data outputs. Similarly, and also quite important, is data assimilation. So that is the use of observational soil moisture and related data to course correct the model as it goes along. In this case, you would be running a model and also taking observational data and doing some comparison and some kind of blending of those two values to find sort of the truer actual soil moisture conditions. In addition, modelers sometimes run ensembles, and that could be either in the form of running the same model multiple times with the idea that through a series of runs, you might become closer to an actual true value or better estimation of the soil moisture value. In addition, there's the opportunity to run multiple models simultaneously, and this way you can take advantage of the fact that different models have different strengths and weaknesses, different areas they focus on, and you might find that the ensemble value of results is, again, more accurate than that which you get from any single model. And then taking that one step further, a number of organizations have developed integrated platforms, and so the North American Land Data Assimilation System, or NLDAS, and the variations there provide a series of models that can be run, a series of different data sets that can be assimilated, and other kinds of support packages for researchers. Another example is the NASA Land Information System, or LIS. So very briefly, here's a NASA Sport LIS model product, just one example. SPORT stands for the Short-Term Prediction Research and Transition Center at NASA, and it provides soil moisture on high-resolution grids for the CONUS, about 3 kilometers, in real time, updated every 6 hours, and it is based on the NOAA land surface model with input from the NLDAS2 atmospheric analyses, so that's using another land surface model package to provide atmospheric analyses, and then the MODIS satellite vegetation as an enhancement to control for vegetation effects. And it provides subcountry soil moisture conditions. Couple images of the output from that product. We've got on the left there the surface relative soil moisture or available water on July 9th, and then on the right there root zone relative soil moisture on the same time. And this would allow you to compare a little bit of what's at the surface level, what sort of immediate, more recent effects of precipitation, for example, etc., versus on the right, sort of the longer term status of the soil column. Like any tool, modeling for soil moisture has certain advantages and some limitations. In terms of advantages, modeling complements in situ data observation because we can't have sensors every kilometer. It provides continuous spatial and temporal resolution, and with that, higher resolutions, in many cases a kilometer or less. With increasing computing power, we'll be able to get more and better outputs from the models, and models allow us to do what-ifs or other types of exploration. At the same time, there are some limitations to modeling. The most basic being that a model is just a simplified version of reality. So there you go on the right, you can see our leaky bucket providing our hydrologic cycle. Of course, modelers are making their models more comprehensive and more complex over time, but complexity brings its own issues in terms of the kinds of bias and error correction that's needed. There's still a question about the quality of forcing data for models. The atmosphere is very complicated, and our ability to really understand atmospheric dynamics is still unlimited. And then in some cases, modeling systems have latency. As the modelers are checking outputs for quality control, quality assurance, that will delay how quickly we can get model results. So that's a quick overview of modeled soil moisture data and products. And just to finish, to talk briefly about blended soil moisture data and products, which would blend all three legs of our stool to provide our soil moisture information system. As you can probably infer from what I've talked about, there's already some overlap in products where our modeled output is using data assimilation and other techniques to bring in observational data. And in addition, remote sense data, in many cases, satellite outputs are fed to models to smooth, etc. So the question for us is, how can we be more intentional about this process? That is one of the objectives of our initiative, to build these blended products that really takes advantage of each leg of our stool. Well, that ends my presentation. Thank you very much.